Okay, thank you so much for attending my presentation. I'll tell you about how to move boundaries in the dilaton-gravity theory to to the 3D form, the double-sided SYK model. The point of our work is basically to give a contribution in terms of the recent developments that they point out that there is a change of relations between different approaches that are answering vascular-affective dual to the double-sided SYK model. Some of them famously tell you that this dual theory is basically the CT space under the conditions that the double SYK model is at infinite temperature and is placed very close to the cosmological horizon at the location called the stretch horizon of the CT space. And moreover, that the theory becomes an hyperfast climber information, basically, that it becomes something that puts out of time order correlators change at a rate faster than exponential growth. So this is in contrast to recent developments that they actually tell you that the dual theory is something else called dilaton-gravity. So the double SYK model is a model with the MIN fermions that have P orthogonal body interactions, where we can put N and P going to infinity, but we keep the ratio fixed. And in that case, it has an absolutely quantum system description after doing the ensemble averaging over couplings between the fermions that has this type of form. However, as I told you, there have been like a recent development that they tell you that they are using canonical quantization, this type of a theory called time dilaton-gravity for this type of a dilaton potential and this type of boundary conditions basically become dual to the double-sided SYK model. And that the metric basically takes the form that they have a black hole horizon and also cosmical horizons, and they like identified with other horizons in the model. Then the question arises of how to reconcile this with the conjecture of SYK, where we have actually an infinite temperature and the theory lives very close to cosmical horizon, and that this is a hyperfast camber. And none of that happens when you actually have the static conditions on the which the dilaton-gravity theory reduces to ds-JT gravity. How do we reconcile these two approaches? Basically, we study a finite curve in the sine dilaton-gravity theory, where we reproduce the same features as the CT space, and we put the theory very close to cosmological horizon or black hole horizon of the dual theory. This is using the form T-squared deformation, the dual theory. So we employ this Hamilton-Jacobi equation that basically relates the finite curve evolution in the system to the energy levels, and this is something that we obtained for this particular choice, for this Euler expectation that we derive. It also requires certain type of thermodynamic properties that agree with those of the CT space, but now they are really finite. And we also see that there are cases of phase transitions using the heat capacity. The system goes between a thermodynamically stable and unstable system, using this type of configurations for the big cleft boundary theory that interpolates between the black hole and cosmological horizon. And there are conditions under which the system is always stable when it's like a very close to cosmological horizon or black hole horizon. However, this phenomenon of hyperfast clambering, basically computing 2-point functions, we can also deduce the behavior of 4-point functions with the periods like out of 10 order. And then we record exactly the type of behavior predicted by SYK. I hope to have given you a flavor of the presentation.